Hello and welcome back to Nunley Math. I'm Aaron Nunley and I am your host for this lesson. We are gradually working our way through a series on solving equations. So far, we've done a video where we talked about the properties that tie algebra together and how those properties are unchanging and predictable. And then we did a video where we talked about how we can begin to use those properties in order to solve single-step equations, and then another video on how we can use those properties to solve two-step equations. Today we're going to take this one step farther. We're going to introduce another property or two and talk about how we can begin to solve increasingly complex equations using the rules that we've already learned. Now I do need to give a special shout out to my buddy Scott, who helped me with some screen resolution issues that we were having. He pointed out that some things were hard to read because we were videoing in standard definition. I believe we've got this in HD now, and this is going to turn out a lot better. Hopefully we'll get an opportunity to go back and refilm some of our previous segments and make them a little easier to read. But thank you, Scott, for that piece of advice. Certainly extra help is always welcome. So, as is good instruction, what I would like to do is I would like to give you an opportunity to go back and review the things that we already know. If you think you remember how to solve this equation, I'd recommend pausing the video, trying it on your own, and then starting the video to see how I solve it to compare the two. It's always much better if you do it on your own, because then you can see the errors that you have a tendency to make. A lot of the errors we make tend to be the same, and if we can begin to spot those errors, it's going to help us to not make them in the future. As for me, I am going to quickly go ahead and solve this two-step equation. We learned that if we have an unknown value and it has been multiplied by 5 and it's had 3 added onto it and it equals -32. If we want to find this value, or the solution to this equation, the value that makes this into a true statement, then we're going to have to go back and we're going to have to try and find some ways to undo all the things that have been done to x. We know from the property of equality that we can make any change to this we want, essentially, as long as whatever change we make is done to both sides. There are some things I can do that will be helpful, there are other things I can do that will not be helpful, but will not change the truth of the equation. In the case of this problem, most of you probably already realize that in order to get rid of the +3, we should use the additive inverse, -3. And we do that because additive inverses always add up to 0. Because of the property of equality, I do that to both sides. And then I compute to simplify that. We intentionally picked a -3 because we knew that a +3 and a -3 would give us a 0. That's the additive inverse. And we like that 0 because we know that adding 0 doesn't do anything, so we can get rid of it using the identity property. That leaves us with 5x equals -35. Now, I do have a times 5 here. I'd like to get this x by itself, which means I want to get rid of this times 5. There's lots of things I can do here, but the best way to get rid of a times 5 is to use its multiplicative inverse, times 1/5, because I know that 5 times 1/5 is going to turn this into a 1. Property of equality says do it on both sides, so I multiply both sides by 1/5. 1/5 times 5 is 1, -35 times 1/5 is -7. Little computation there. I have my 1 and my -7. Now, we intentionally made this a -1 because we know 1 times anything stays the same. That's the identity property, and we can know that our solution here is x equals -7. Now, I'm not going to spend much time on it, but up here in the corner, I have gone through and done a check. 5x plus 3 equals -32. We rewrite the original problem. Substitute in the -7 we said would work. Simplify. Simplify again. When the two sides match, we know we've solved the problem correctly. We have found the value that would make the statement true, and we put a little check mark there so that we don't forget. Now, I am going to introduce a new idea to you in this video that's going to help us with our more complex problems, but to do it, I'm going to tell you a little bit of story. A certain video game you enjoy is free from the online application store. However, the manufacturer earns their money by making microtransactions within the game where users purchase upgrades and enhancements that assist them as they progress through the game. So let's say that buying a preeminent outfit costs 2,000 bucks in bucks. There's our preeminent outfit. And a heroic weapon costs 800 in bucks. You and two friends each decide to buy 2 outfits and 4 weapons. What mathematical expression could you create to represent the total cost in bucks? And can you create a second different expression to represent the same cost? Now, if this were my classroom, I would actually present that problem to small groups of students and give them some time to work that out on their own. As this is a YouTube video instead, I'm not going to have the opportunity to do that. I think it's better if students generate those ideas on their own, but we can talk about the conclusions that students tend to draw. Most of the time, students will fall into one of 2 categories. They will either find the cost for each item and then add them up, or they will find the cost for each person and then multiply that by the number of people. I want to look at that for just a second. We're going to look at both of these. Let's start over here on the left with the cost for each item. In this particular story, we have 3 people. The 3 people are buying 2 outfits at 2,000 in units apiece. And those same 3 people are buying 4 weapons at $800 apiece. That means that each of those 3 people is going to spend $4,000 on an outfit, and each of those 3 people is going to spend 3,200 in bucks, I think I said dollars, in bucks on the weapons. Which means altogether, we're going to spend 12,000 in bucks on outfits and 9,200 in bucks on weapons, for a total of 21,600 in bucks. The other group of students usually do something more like this. We have 3 people, and the 3 people each buy 2 outfits at 2,000 in bucks each, and 4 weapons at 800 in bucks each. Notice we have 3 people, and each of the persons is buying all of this. So, for the 3 people, each of them spends 4,000 on outfits, and each of them spends 3,200 on weapons. Or, in other words, each of the 3 people spends $7,200 for a total of 21,600 in bucks. Notice in this story, one way we were thinking about the cost of each item. Over here, we were looking at the cost per person. Both ways are equally correct. We both get the same exact answer. We're just learning to organize or think in different ways. And that's actually a very, very good thing. It leads us to something known as the distributive property. In formal algebraic language, we would say A times the quantity B plus C equals AB plus BC. And most of my students would look at me like I was crazy when I gave them that formula. But in very simple language, it says if you have several copies of the same group, you have several copies of every item in that group. And kind of a hybrid between the 2 types of language, you could say the product of a sum is the same as the sum of the products. Once again, most of my students are still pretty confused at this point. So here's how I would break it down for them. I'd give them this example. If I say to you 5 times the quantity 3 plus 4, we need to think about what this parenthesis says and what multiplication says. Just like in the last problem, the number that's on the outside here is talking about how many groups I have. I have 5 groups. Remember, groups are the parentheses. And inside of those groups, I have 3 of something, and I have 4 of something. So 5 groups, each group has a 3 and a 4 in it. As a picture, I could do it this way. Here's a group of 3 and 4. 2 groups of 3 and 4. 3 groups of 3 and 4. 4 groups of 3 and 4. And then you have 5 groups of 3 and 4. It's one way to think about or illustrate this relationship. Over here on the other side, I'm going to do what looks more like the right side of this equation. Notice here on the left, 5 times 3 plus 4 says I have A on the outside, B plus C on the inside, matches here. When I say 5 3s and 5 4s, I'm organizing this information in a different way. Instead of having a group of 3 and 4 5 times, I just have 5 groups of 3 and 5 groups of 4. Notice, if you compare the picture over here on the left to the pictures over here on the right, you can see that over here on the left, you can actually see the 5 groups of 3 and the 5 groups of 4. If you look over here on the right, you can actually see across that top row a 3 and a 4, a second 3 and a 4, a third 3 and a 4, a fourth 3 and a 4, and a fifth 3 and a 4. This is the exact same number of items. The only difference is over here on the left, you get 5 groups of 7, which is 35 V-bucks. 5 groups of 7. Over here on the right, you have a group of 15 and a group of 20, which happens to also be 35. Regardless of which way you group the information, you come up with the exact same number of V-bucks. That's the point of the distributive property. Now, I don't normally do this in my algebra class, but in my pre-algebra class, or my 7th grade advanced math class, I actually show a couple different illustrations that might help. If I wanted to say the distributive property in plain language, or give an example, I might say having 3 groups is the same as having 3 of everything in that group. So for example, let's say I have 3 reindeer, 3 elves, and 3 Santa Clauses. 3 reindeer, 3 elves, and 3 Santas. Over on this side, I have 3 groups, and each group has a reindeer, an elf, and a Santa. Notice both pictures have the exact same thing in them. We've just changed the way the information is grouped. Over here on the left, I have 3 reindeer, and I have 3 elves, and I have 3 Santas. All the reindeer are together, all the elves are together, and all the Santas are together. But over here on the right, I have 3 groups, and each group has 1 of each. 2 different ways to represent the exact same story. Here's another one I would give them. Having 4 groups is the same as having 4 of everything in that group. So, if I were to give you this picture, I have 4 Batmen, 4 Spider-Men, 4 Hulks, and 4 Thors. You wouldn't believe how long it took me to decide whether those were Batmen or Batsmen or Batmans or Spider-Mans. But regardless, this is what I finally came up with, correct or not. If you're not sure, or if you know better than I do, you can feel free to let me know in the comments section. Over here on the right, though, I have 4 groups, and each group has a Batman, a Spider-Man, a Hulk, and a Thor. Notice I have the exact same figures here on the left, and as I do here on the right, I've just reorganized it. Over on the left, I have 4 Batmen, and 4 Spider-Men, and 4 Hulks, and 4 Thors. Whereas on the right, I have 4 groups, and each group has the exact same thing in it. 2 different ways to organize or think about the exact same information. Now, if you were in my pre-algebra 7th grade advanced math class, what I would end up doing then is I would give you a task in the evening at home to go ahead and create your own story kind of like this, where you either went on the computer and printed things out, or you went to a magazine and cut pictures out in order to create your own story. You could have also drawn them. And then the next day we would show those in class. The important thing is building that connection that this is purely an organizational exercise. We're not changing the number of items, we're simply changing the way we look at it. Why do we go to all that trouble? Well, if I were to give you this story, 5 times the quantity, x plus 32 equals 48. I can use this lesson on the distributive property to solve this equation, because I have 5 groups, and each group has an x in it, and each group has a 32 in it, and when I total that, I get 48. We're trying to solve this equation, or find what number we can stick in there for x that would make the statement true. Now, this is our original or given problem. Here's what I'm going to do. At the very beginning, I'm going to reorganize this information. Since this has 5 of each, I'm going to use the distributive property to just say 5 of each. 5 x's and 5 32's for a total of 48. That's the distributive property. I'm then going to go ahead and simplify this 5 times 32 using some computation. And when I do that, it turns into this familiar two-step equation form. Now, we've done this several times, and you're going to find that as I do it quicker and quicker each time because we should be getting better and better at it. The goal is to be so good at these that as soon as we see that form or that pattern, we can almost do it without thinking so that we can focus on more important things. We don't want to exert a lot of energy here. So, if you are struggling with this, you're going to want to watch closely. If you feel pretty confident that you can solve a two-step equation, pause the video, try it yourself, and then come back and watch me. Here we go. To get rid of the plus 160, I'm going to use the additive inverse. Notice I wrote it beside it this time instead of underneath it. It doesn't change anything, and in our very first video I said you could do it both ways. I intentionally did it this way this time so that I could have this lining up with what rule allowed me to make the change. Property of equality says I can do whatever I want. And then I do some computation to simplify. I intentionally chose the additive inverse to get the 0 because adding 0 doesn't do anything and I can get rid of it. That's the identity property. I have that 5, I want to get rid of it, so I'm going to multiply by the multiplicative inverse, which is the 1/5. A lot of you would say to get rid of the times 5, divide by 5. Multiplying by 1/5 is the same as dividing by 5, so that's perfectly acceptable. I like to write it this way in the video because I want you to see it's the multiplicative inverse. And then I'm going to use some computation. When I'm finished, I have that times 1. I was intentional about picking 1/5 in order to get the times 1 because I know multiplying by 1 doesn't do anything because of the multiplicative identity. And we're done. Now, take a look right here. This equality computation identity is going to keep coming up over and over again. In fact, once I can turn something into a two-step equation, it almost always finishes with an equality computation identity. Those 6 steps are fairly common and consistent. Occasionally, I've got another step underneath that we'll talk about farther down the road, but for the most part, if you do your distributive property early on in the problem, and then you just simplify things a little bit, you usually can get something that's very predictable, making your job a whole lot easier. I made a little note over that. Equality computation identity happens over and over again. Let's do another one of these. This is very similar. I am going to give you an opportunity to go ahead and pause the video, try this on your own to see if you understand. Once you're done, restart the video and you can see my steps and solutions. I'm going to go ahead and do that now. That's my original problem. Since I have -3 groups and each group has a 2x and a 13 in it, I'm going to distribute that -3 to both. Distributive property. I do a little bit of computation there to simplify that, and now it's in that familiar two-step equation form. Once that happens, as soon as I recognize that, it's very easy for me. Property of equality, computation, identity, equality, computation, identity, and there's your solution. Just see it again? Equality, computation, identity, equality, computation, identity happens a lot. There is one more application of the distributive property that we want to be make sure we're aware of, and that is one that's a little less easy to spot, a little less easy to recognize, and that's this. In this problem, we have 5 x's and 2 x's. We have x of 5 and we have x of 2. I have x of these and I have x of these. The distributive property says if I have x groups, I have x of everything in that group. In this case, if I have x of everything in the group, that means I must have x groups of those things. That's the distributive property. Most people don't explain it that way. Most people explain it as combining like terms. But either way, you end up with a 7x plus 11 equals 95. 7x plus 11 equals 95, using some computation. Notice it's that familiar two-step equation form: equality, computation, identity, equality, computation, identity. Notice it appears twice. It happens all the time. One final thought for you today. There are no secrets to success. It is the result of preparation, hard work, and learning from failure. That is a quote from Colin Powell, the former Secretary of State of the United States of America. Once again, thank you for watching. If you found this helpful, please make sure you tell me in the comment section so that I know that somebody's watching these and I can continue making them. Please be sure to like and subscribe, and also to turn on your notifications so that you'll know when new content is being put up. I am trying to get these put out for you in order so that you can learn along with my class, and so that my class can use these as review tools as we're working through the curriculum as well. Thank you so much. I look forward to talking to you again soon. Have a great day. Bye-bye.